Welcome back. Did you learn something interesting? I hope so. Okay, so let me, as this is the last activity, kind of, wrap up and bring everything together a little bit. Why did we talk about Conway's Game of Life in this context here when really it's about, computer science and programming and things like this? Well, really because I find this a very nice way to get acquainted with the idea of programming without necessarily starting to do a programming as such, because as I'm sure you're familiar with, programming itself is kind of daunting to start with, right? You have all this, okay, I need some text here, or maybe I can move some blocks around, but then I kind of still really need to think about this. Whereas this is more of a playful way to explore some of the ideas behind programming by just specifying these dead and alive pixels and then seeing what happens with them. And as we've talked about, this is actually equivalent to how a computer under everything that you're working with works, because in the end, the code that you write or the blocks that you put together or whatever you might be doing to control what a computer does results in a sequence of zeros or ones, the bits that determine not only the data that the computer operates on, but also the instructions, because as we've also talked about, data and code are actually the same. They're stored in exactly the same way in a computer, and this is kind of what we have here in Conway's Game of Life, where the rules of the Game of Life, the equivalent for an actual computer, are the rules of physics that determine what happens if I put components together in this particular way and then apply a current and a certain voltage. Where do the electrons move, and then based on that, what happens at the really high level where you're actually sitting down in front of a monitor and you're typing on a keyboard, or you're touching a screen or something like that to manipulate what happens. So a nice way to kind of get into this general mindset of programming a computer, of doing things that affect how a computer works, but also something that you can do even with relatively young children, because it's kind of playful, right? You just specify these patterns and then you click a button and you see what happens with these patterns. And sometimes it's really quite cool, right? So you get these kind of growing things and moving things, and then it might collapse at the end and just really disappear, which is kind of disappointing, but hey, sure. And as we also talked about, kind of mirrors how computers work, right? You make a very small change and you have a very large effect, and you might not have expected this effect at all. All right, a couple of things I wanted to highlight in the Wikipedia article that you have just perused. Particularly, this is the section here on undecidability, because this is really very relevant in terms of theoretical computer science and in terms of some of the fundamental models of how computing and computers work, but also some of the fundamental limitations. So the first thing is essentially related to what I've mentioned several times now, that even small changes can have a large effect, and it's really, really difficult to predict what's going to happen with a particular pattern. If I show you a particular pattern, unless that is really kind of trivial, it's hard to even tell whether this is going to converge to something stable or to one of these oscillators, or maybe it's going to be one of those spaceships that we saw that essentially keeps moving and moving, or is this just going to move about in a chaotic kind of fashion until eventually it stops, and if so, when is it going to stop? As it turns out, and as you've read about in this section here, this is actually an undecidable problem, which means that in general, there is no answer to this. We cannot determine, apart from obviously running the program and then stopping after a certain number of iterations to see whether it's still doing something, whether this will behave in a certain way. So this is the halting problem, which is one of the really fundamental theorems of computing that tells us the limits of what we can do with at least these kinds of computers in general. So they're not as powerful as you might think, and there are various thought exercises that might be suitable for a more advanced classroom that you can do there. The second thing I want to highlight is essentially the last paragraph in this undecidability section here, this idea of a universal Turing machine And you can go to the linked article here and read up on this, but essentially it is a theoretical construct that allows us to show that the kind of computers that we're working with are capable of computing any function. And this is important because we don't know what exactly we want to program. In particular, we don't want to develop a computer and then find out that, oh, this particular program that I want to write, this particular problem that I want to solve, I, for whatever reason, cannot solve using this particular type of computer. That would be really kind of frustrating, right? You don't want to buy a laptop and then find, oh, I can't do this particular kind of sum with it, or something as fundamental as that. You would ideally want to know that before you buy the computer. This is why this construct of a Turing machine is important, because that essentially allows us to say that, yes, at least in principle, this particular machine, this laptop that you just bought, is capable of computing any function. Now, of course, whether I can do this in practice, whether a program exists, and if no program exists, how difficult it will be to come up with a program is an entirely different matter. So this is a theoretical construct. This doesn't tell you that it's easy to write a program to do the particular thing that you're interested in, but it tells you that, at least in theory, it is possible. And it might be very difficult. Obviously, people spend a lot of effort developing programs, and this can take years and years to develop software that does a particular thing. But hey, at least we know that it's possible. In particular here, the relevance of this particular paragraph is that Conway's game of life is actually able to emulate such a universal Turing machine. So as I said before, we can use this really quite simple game with a small set of simple rules to do anything we might want to compute. Of course, there's a lot more to this in practice. So in particular, if I wanted to, for example, add up two numbers in Conway's game of life, I have to decide how exactly I want to encode those numbers in terms of the bits that we have in this particular representation, so living cell or dead cell. But that's essentially exactly the same thing that happens in real computers as well, because, as I said, at the most fundamental level, the bits on and off, alive or dead, it is what we're working with there. And people have solved exactly the same kind of problems. But main point really being that while Conway's game of life may seem very simple and kind of more like a game, as the name in fact suggests, than a serious educational tool, you can do serious stuff with it. And you can do arbitrarily complex things that essentially allow you to do exactly the same things that, in principle, your laptop and other computers are able to do. So again, something that you might be able to use in a more advanced computing or computer science class, where you can talk a little bit about the background, a little bit about the theory, instead of just talking about programming. All right, that's it for me. I hope you had fun with this set of activities on Conway's game of life, and I hope that you can take at least some of this back into the classroom and get some of the enthusiasm that I hope I was able to get across for computer science and for programming to your students. Thanks.